Hello and welcome everyone. So in this video we are going to solve some problems, and these problems are from a great book on electronics called Electronic Circuits and Devices by Boylestad, and this book can be found on archive.org. I think the 10th edition of the book, or 11th maybe, and this is a really probably the greatest book that you can have for learning electronics, and it's really undergraduate basic undergraduate level electronics. So if you are on an undergraduate electronics engineering course, or even if you are a hobbyist learning electronics, this is probably the best, not probably, but this is the best book that you can go and to learn electronics. So in this book is full of good and great exercises, and I have taken a few exercises from the book on the diode sections, and this is for my playlist on diodes on my YouTube channel. So the circuit that we're going to solve will be, so we'll start with a few basic diode circuits just to figure out the currents and voltages on here, and then we'll go on to clipper circuits, and then after that we'll go to some clumper circuits. So I'll explain what those all mean. So let's start with the first exercises. So this exercise asks us to determine the current I on this circuit. So there are three exercises on here. So we start with the first one here, exercise A. So we have here on the left a voltage source, which is pointing downwards here. So the plus side is downwards. So we have a silicon diode here and a 10 ohm resistor here, and the current is flowing to the right here. So let's first of all remind ourselves that the silicon diode has a voltage drop of 0.7 volts. So it needs, in order for it to be forward biased, it needs 0.7 volts from plus to minus here. So the minus side, of course, is the one that has the little bar there. So let's determine the current flowing here. So the first thing to notice here is that this diode is reverse biased, because if you look here on the voltage, the minus side is attached to the plus side of the diode, so it's reverse biased. And if you remember the a reverse biased diode, so we have the diode here, we have the P substrate here and the N substrate here, and we need, for it to be forward biased, we need a positive voltage on the plus side here. So if you look, the diode looks like this. This is the positive side, this is the negative side. So in order for it to be forward biased, we need a positive voltage on the positive side. Here we do not have that, so the diode is reverse biased. So this is an open circuit here. You can imagine that this diode is not here and the circuit is open here. So if the circuit is open, there is zero voltage across the resistor and therefore zero current. So in this case, I is equal to 0. Okay, so let's go to exercise B. So on exercise B, we have a 20 volt voltage source here. And if you look at the direction of the voltage source, if the plus side is on here, so the plus side will appear here, and so we have a voltage on this direction here, and this first diode here is forward biased, so it's a short circuit. Here is the plus side, here is the minus side, so we have to figure out the current on this direction here. So the current on this direction here is going to be equal to the sum of the current in this direction and the current on this direction here. So we can see for this first resistor, the voltage here is 20 volts, and the voltage here, because there is a 0.7 voltage drop across this resistor, the voltage here is going to be equal to 19.3. And so the current, remember Ohm's law, is V is equal to IR, so I is equal to V over R. So in this case we have 19.3 divided by 20 ohms, and if we open the calculator here, we have 19.3 divided by 20, and this is equal to 0.965, so 0.965 amps. So this is the first component on this direction. So now we figure out the currents on this one, so it's the same thing. So we have 20, this diode is also forward biased on this direction. So here's the same thing, we have 20 minus 0.7, which is 19.3, and the resistor is 10 ohms, so 19.3 divided by 10 is just 1.93 amps. So the current here is 1.93 amps, and the current here is 0.965. So if we add them together here, 0.965 plus 1.93 is equal to 2.895 amps, and this is I, so I is equal to that. So this is done then. So on the circuit on the right here, C, we have a voltage source here, 10 volts in this direction here. So this diode here is forward biased. However, this diode here is reverse biased, so this is an open circuit here. So this side here you can neglect, and so we have 10 volts here on this resistor, and the resistance is 10 ohms. So 10 divided by 10 is equal to 1 ampere. 1 ampere. Okay, so as you can see here, we need a forward bias on a diode for it to be open. So if we want to revise the structure of the diode, then we have here we have the P side here and the N side here. For the P side, we have holes which are the charge carriers here. So they have positive charge. Each hole has a positive charge. On the negative side here, we have free electrons, lots of free electrons, and this diode will have a depletion region on here, which on this side is positive and on this side is negative. So in order for us to overcome this depletion region, we need to also this this depletion region creates an electric field in this direction. The electric field always goes from the positive side to the negative side, and that's the direction that a positive charge would move under the influence of the electric field. So we have an electric field on this to the left here. So without a voltage on here, these positive charges cannot flow to this side here, because of they have to overcome this electric field, and they don't have enough voltage and pressure on them or energy for them to overcome here. So they do not go on this direction here. Very little of these charges will fly here. So we need a positive voltage on here, negative voltage on here, and when we do this, we have a voltage here. This voltage will create an electric field in this direction, which has to be larger than this electric field, and therefore that's why we have the 0.7 volts drops here. And after that, we destroy this depletion region and charges can flow on here. So that's the diode. So let's go on to the next problems. So these problems are about clippers. Now, what do clippers mean and what do they do? Clippers will they will clip, or they will kind of remove part of the voltage on the signal here. So if we have a signal, for example, like that, we can have a clipper that will clip off this part of the wave. So we would have a wave that, for example, would look like this after going through the circuit. Here it would be flat, and then it would go down again, and then we could have another clipper that clips half of it, and it goes back like this. So it just removes part of the signal like this. You could also have other clippers that take square waves. So you have a square wave like this, and the clipper would remove the top voltage here, for example, and then we will have a signal with lower amplitude and so on. So this is what these circuits here are doing, and so we'll do this for this signal here. So let's do exercise 32, and let's look at the first circuit here on the left. So we have VI, which is the voltage source, and so this would be a voltage source like this, and we have VI here, and these two are connected together. And so we have a sine wave with amplitude 20 volts here on this direction here. So what happens is the voltage is first positive and then it goes negative. So on the positive side, the voltage will go like this on the circuit, clockwise like this. And so if you look here, this diode, when the voltage is positive, is reverse biased, because we have the positive voltage on the negative side. And so for the positive part of the wave here, this diode is open. So it's an open circuit, so the voltage here will be 0, because we are only taking one side of the voltage source. So for the if we sketch the response of the circuit here, for the first part here, the response will be 0, there will be no voltage. Now for the negative part, let me take a different color here. For the negative part, the voltage will be in the opposite direction, so it will go like this. And for this, the voltage will be 20 volts in this direction. So this will be the plus and minus will swap, so this will be plus, this will be minus. And so here we have just a positive voltage, 20 volts on the counterclockwise direction here. So this 20 volts will appear here, and here, because of the 0.7 volt drop on the diodes, the voltage here will be 19.3. And so the voltage here, the voltage here will be 19.3, sorry, after the diode drop. So the voltage from here to here will be, because the polarities here are reversed, remember that this voltage has its plus side on here and the negative side on here. So the voltage V naught we're looking for is the opposite of that. So the voltage here will be minus 19.3 volts. So V naught is equal minus 19.3 volts. So that's that. And now let's look at this circuit over here. So if we sketch the response on here, so this is time and this is V naught. So let's look at this. So again, on this circuit here we have 20 volts. So for the positive side of the circuit we have 20 volts in this direction. And now the first thing to notice here, we have also a voltage source here. Have a voltage source on this direction. This voltage source will automatically forward bias this diode here, and because the direction of this voltage source is in this direction, and it's 8 volts, so larger than 0.7. And also this diode here is ideal. An ideal diode doesn't have the 0.7 voltage drop, so it has 0 volts voltage drop, 0 volts across it. It's just a short circuit when it's forward biased. And so on the first cycle, when the voltage is positive, we have a positive voltage here, and this voltage will start at 0. When the voltage here is 0, we have a short here, and then 0 will appear on this here, and then we have 8 volts here. So this 8 volts will forward bias the diode here. So diode is forward biased, so if we have 0 volts here, and we look at the voltage on this direction on the resistor, anti-clockwise, we'll have 8 volts on this direction, so 8 volts here, 0 volts here, so the voltage here will be minus 8, so we'll be somewhere here at minus 8 when the voltage is 0, for example, the first point here. And so when the voltage here is larger than this, larger than 0, then we'll start to force a voltage in this direction here. And so as long as the voltage is less than 8 volts, this diode will be forward biased, and then we'll have that voltage appearing across this resistor here. And so, for example, if we have 4 volts in this direction, we'll still have 4 minus 8, which is equal to minus 4, so the minus 4 will appear here, and so on. So as the voltage starts to increase, we'll have a voltage that goes like this. So this will be minus 4, for example. And so when the voltage is equal to 8 volts on here, on this, so a point here, more or less 8 volts here. So when the voltage is exactly equal to 0 volts, the diode will become reverse biased in this direction, and so that will be an open circuit because we have 8 volts on this direction, minus 8 volts, so we'll have 0 volts here at this point here on the diode. So 0 volts here, this diode will be open, and then if this diode is an open circuit, then the voltage will become 0. And so when the voltage is equal to 0 volts, then we'll have a 0 voltage on the diode that goes on the 0 axis here. So this is 0 volts. When the voltage is larger than 8 volts, then, and up to 20 volts, we have 0. So it should go something like this, but we'll clip it like this at the top when the voltage is larger than 8 volts here. So 8 volts here, some point here. So then we'll go back when the voltage is again equal to 8 volts will appear at this point here. And so when the voltage is less than 8 volts, this diode will be forward biased and will have whatever voltage is there will appear in here until the point that we have, for example, back to 0 volts. At 0 volts we'll have this diode forward bias, so we'll have minus 8 volts here again. So when the voltage is less than 0 volts on here, then this voltage will add up to this 8 volts in this direction here. And so let's suppose that we have VI in this direction. So whatever VI is in this direction here will be added 8 volts, will add 8 volts to it. So this will appear as a negative voltage on here. So we'll have VI minus 8 in this direction. So this is 8 and we'll have VI minus 8. So the point here is minus 8 for when the voltage here is 0, and the voltage being less than 0 will go below minus 8, and so on until it goes back to there. And I have a little simulator here for us to try this circuit, so we can build the circuit on this simulator and look at the response to see if it's correct. So here we can add a voltage source, an AC voltage source. Then we can add a constant DC voltage source in this direction and make it equal to 8 volts. And so also this voltage here is 20 volts AC. So okay, and now we add the diode. So the diode in this direction, we add the resistor, complete the circuit, and this is the output voltage. So we also add the ground, which is our reference point. And so if we look now at the response, we can just probe this. Before that, let me just adjust the bias on this resistor. So this resistor here is ideal, so the bias is very small. So let's do 0.01 volts, like that. So, and here we probe the voltage on the resistor. So let's take it from reset. Let's actually, before this, let me probe the voltage source. So the voltage source will be like this. So the voltage source, as you can see, is a sine wave, amplitude 20 volts. So if we probe the voltage of the resistor after the clipping, as you can see here, look at the response. It's shifted downwards and the top is clipped. We clip some voltage from the source, so it's exactly what we have here. So we can say that we are correct. So here we have another example. Here we have a square wave, amplitude 20 volts, and we're just looking at this circuit here. So remember, we have a voltage source here, VI plus and minus, and here we complete the circuit. So we're looking at the voltage here across the resistor. So look at the polarity of this resistor here, and it's a silicon resistor, so 0.7 volt drop here. So when the voltage here is 20 volts, then this diode is forward biased, and the voltage appearing here after the diode will be 12 minus 0.7, which is 11.3 volts. So we'll have 11.3 volts, and the voltage here will just be a resistor divider relationship. So this is 11.3 times 2.2k divided by 2.2k plus 1.8k. So here we just want to look at the overall idea. If you want, you can go ahead and calculate this number, but it's not necessary. I'm just looking at what is the response here. So the response here will be equal to, so this is going to be a ratio of this voltage, so it's going to be a smaller voltage here, just a small part of the voltage. So as you can see, the voltage has been clipped. And so when the voltage here is minus 12, so we'll have a voltage in this direction. So minus 12, we have the plus here and minus here. Or you can imagine that the voltage here is plus here and minus here, and this is 12. So just reverse the direction. So let's say that we have minus 12 in this direction. So if we have minus 12 here, this diode is just reverse biased. So no matter what we do, this is just reverse bias and open. So this is going to be 0 volts. So just we are just here, so the response is just going to be something like this. So we clip off the bottom of this voltage, and also the top is clipped off. So that's the response of that circuit. So now we look at this circuit here. So same thing, voltage source here, plus and minus, and this complete the circuit here. Silicon diode, 0.7 volt drop. So when the voltage, and also notice that we have a voltage source here, a DC voltage source. And so when the voltage is 12 volts in this direction, this diode here is forward bias, and here we add 4 volts to the 12 volts because it's a voltage source in this direction. So the voltage appearing here is going to be 16 volts in this direction. So we have this, and then we have 16 volts here. So now we look at the opposite case. So when the voltage is reversed on the counterclockwise direction, we have minus 12 volts from here to here, or you can see it as 12 volts in this direction here. So if we have 12 volts in this direction, then we have 4 volts here opposing that direction. So the voltage here is going to be 12 minus 4, which is equal to 8 volts. So we have 8 volts in this direction, and 8 volts in this direction will reverse bias this this silicon diode here, and in that case the voltage is just going to be 0. So this is almost the same as this, but instead of clipping it off, clipping it downwards, we're clipping it upwards. We're adding some voltage here. So if we look at the simulator here, let's start a new circuit, and this will have a voltage source here, which I'll change to a square wave with 12 volts amplitude. We have a silicon diode on this direction, and we have a voltage source of 4 volts in this direction, and then we have a resistor here, and this. So so if you look here, this is the input voltage, and if we look at the resistor here, we have just this the same, but we clipped the bottom off and added some voltage, almost 4 volts, except we have the 0.7 drop across this, so it should be 15.3 and so on. Okay, so that's that circuit, and now we look at clumpers. Now clumper circuits are very interesting circuits because they allow you to take an AC voltage and shift it either upwards or downwards. And so this is what clumping means. It means just to shift the voltage upwards or downwards. And for this we use capacitors. This is a very interesting circuit because we use the capacitors as a source of DC voltage to add up to the AC. So you could also do this with a voltage source, for example. You could replace this capacitor by a simple DC voltage source like this, plus or minus, or in the opposite direction. But sometimes you don't want to waste a voltage source in the DC voltage source. You don't want to add. It's much easier to just add a capacitor to here in order to shift your voltage. And for this we also use the diode. So let's look at what happens on this circuit. Let's look at the response. So this is T and this is V naught. And so this is a square wave input, 20 volts amplitude. So on the first cycle, it's going to go on this direction here, clockwise direction. Now on this first cycle we have 12 volts on this direction. This diode here will be reverse biased. So this capacitor will charge up through the resistor. Now the point on this clumping circuit is that we need to make the RC constant. RC very large. Very large. So this resistor here is very large. This capacitor here is large. So that it has very little chance of discharging or charging in between these cycles here. Otherwise there will be no points to the circuit because the capacitor would charge and discharge really quickly, and that wouldn't add any DC voltage to the circuit. So this must be large. So that's the first point. So in that case, on the first cycle, on this direction, the capacitor will not have time to charge through the resistor, so it's just going to be 0 volts. So now in the next cycle, when the voltage is negative or in this direction, then the capacitor is going to charge through the diode because the diode will be forward biased in this direction. the capacitor will charge up really instantaneously through the diode, because this is just a short circuit. And so the capacitor will charge to 20 volts in this direction. So we have 20 volts in this direction, which is equivalent to minus 20 volts in this direction, here. So in this cycle here, anti-clockwise, we have charged the resistor through the diode to minus 20. So now this is where the effect comes in, because now in the next positive cycle on this direction, what will happen? This diode is reverse biased, and so the voltage here will appear on the resistor. So what voltage will appear on the resistor? So if we use Kirchhoff's voltage law here, we have VI on this direction, so we can write down the expression for a Kirchhoff's voltage source. So we have VI. So VI, this is plus and this is minus. So when you have a voltage source here and you have another voltage with its plus side matching the plus side of your voltage source, you take this voltage, you subtract this voltage to get the final voltage at this point. So because this voltage is negative, then we have VI minus, so this voltage here is VC, voltage across capacitor. So Kirchhoff's voltage law is VI minus VC, and then here we have V naught, which will be minus V naught is equal to 0. Minus V naught because we are going from plus to minus. So VC here is minus 20, so we have that VI plus 20 minus V naught is equal to 0, because minus times minus is plus. So VI plus 20 is equal to V naught, and so V naught is equal to VI plus 20 volts. So on the positive cycle here, we have the voltage here 20 volts plus 20, which is going to give us 40 volts. So 40 volts in here. So that's on the positive cycle. So then we'll look at the negative cycle. So the voltage will be going this way now, anti-clockwise, and so we'll have VI in this direction. VI in this direction here. So if we look at Kirchhoff's law in this case, we have here VI, and then the voltage here on this on V naught here. Actually, let me do this as minus VI. So we go on this direction here. So we have VI here, which is going to be a negative voltage. So it's VI is equal to minus 20. So we have VI minus the voltage across capacitor here, which is plus 20, and then here we have minus V naught is equal to 0. So then we have minus 20 plus 20 is equal to V naught, and V naught is equal to 0. So on that cycle we have here V naught is equal to 0. So as you can see, the waveform is going to just be like this, and this is the effect of clumping. We just have shifted this signal here upwards by 20 volts. So the axis used to be here. So this would be minus 20 and this would be plus 20. But because we have shifted upwards, then we have 40 and 0. Okay, so we have solved this one. And now we look at this circuit here. So we have the voltage VI here, plus and minus, and the circuit is completed here. So we look at V naught. So same thing here, except we have a voltage source just below the diode here. So when the voltage is clockwise like this, same thing, the diode is reverse biased, the capacitor will not have time to charge because this RC is really large. So then we look at the anti-clockwise voltage. So here we have VI, and so for this diode here will be forward biased because the voltage here is greater than 5 volts. So this diode will be reverse bias, and this capacitor will charge in this direction here, with here plus and here minus, and this is equivalent to charging it in this polarity plus minus here. And now if you look here, the diode will become a short circuit here, and the voltage VI, which is 20 on here, in this direction, 20 minus 5 will just be 15. So the capacitor will charge to 15 volts here in this direction, which is equivalent to minus 15 in this direction. So instead of charging it to 20, to minus 20, we charge it to minus 15 because of this voltage source. So then we look at in this direction here for the next cycle, the positive cycle, and then using Kirchhoff's voltage law again, we have VI plus 15 minus V naught is equal to 0, or V naught is equal to Vi plus 15. So we can see that this is going to be exactly the same thing, except that we are shifting this only by 15 volts instead of 20. So we have here we have 35, and here we have 5 on this direction. So this will be minus 5, and so this is the response. So I'm just doing it quicker, so because it's exactly the same as here, and we get the idea that we are shifting upwards by 15 volts, and so that we are adding 15 volts here, so minus 20 plus 15 is minus 5. So that's the response for that circuit. Okay, so this is the next clumping circuit, and here we have a sine wave rather than a square wave, and so here we can sketch it again. So it's the same thing, just slightly different. So on the positive cycle here, the diode reverse bias, again capacitor doesn't charge. So then we look at the counterclockwise direction here, and so then on here we have on the negative side here we have Vi in this direction, charging the capacitor to minus 120. Guess you get the idea. And so then we look at the positive cycle again, and we'll have here Vi plus 120 is equal to V naught. So as you can see, we have shifted the voltage Vi by 120 volts. And so if we have 120 here, then the sine wave is going to be shifted upwards like this. So like that, and goes to 0, and then goes to 240. So here's 240 volts, and here is 0 volts. Because remember, when the voltage is minus 120 here, then minus 120 plus 120 is equal to V naught. And so here on this circuit we can sketch it also. And now look here, the diode here is on the opposite direction to this. So as you can see, we are going to be the opposite. So this is going to shift the sine wave downwards by minus 120. So if you imagine minus 120 here, the first step is to see that it will shift it downwards like this by minus 20, because the diode is reversed. But here notice that you have a voltage source here with plus sides on with the plus side on top. So if you look here, the capacitor, when this is in this direction, or actually sorry, it's in the opposite direction, so the capacitor will charge when the voltage is in this direction. So it will charge to 120 minus 20, so that's minus 100. So instead then of 120 here, the voltage will be shifted by will be shifted just by 100, by minus 100. So we have this is 0, this is minus 100, sorry, minus 100. So the voltage, so this is the new axis for the source, and so the voltage will go like this. So we have 20 volts here, 20 volts on left on here. So this is what clumpers do. So they just shift the voltage either upwards or downwards, and you can add an offset here with the DC voltage. And so this is what I wanted to do for today, and so I hope you have enjoyed, and thank you very much for watching. And the next videos I'll be solving more circuits, and I'll be introducing more concepts about diodes. So if you have enjoyed the video, please don't forget to subscribe, and thank you very much for watching.